Hey everyone, in this final video for section 8.3, we're going to introduce our final theorem and look at an example where we're practicing using it. So our final theorem is called the ratio test. So for this test, we're starting with one series, so a series of an terms. So I can write that out, n equals 1 to infinity of a to the n. And what do we do with these series? But we consider the limit of the ratio of the terms. So we take the absolute value of the an plus 1 term over an term. And when we take that limit, we get some value r. Now, I'm not saying r is finite here necessarily, but there are three different categories for r that are going to determine the convergence or divergence of our series. So if that r is bigger than or equal to 0, but less than 1, then the series converges. If the r is bigger than 1, then the series diverges. And then the final situation, if the r is actually equal to 1, then the test is inconclusive. Which means that this test will not provide us with a result or a conclusion about the series. So I just want to kind of talk about why this theorem should make sense. So let's notice that when we're computing this value here, an plus 1 over an, we're computing the ratio of consecutive terms. And notice in our categories here for a and b, we have two distinct categories when r is between 0 and 1 and when r is greater than 1. So where are we seeing a theorem or a series in which we are broken up into convergence or divergence based on if a value r is less than 1 or bigger than 1? Well, we've seen that in the geometric series. So in a sense, what this is saying is that if the limit of the ratios becomes some r in the limit, then the series and that r, or period, becomes some r, then that series is approximately a geometric series. So then we can use that r to determine convergence. Okay, so I'm going to write that down in this note. So observe that if this limit of the absolute values of the ratio is r, then for n, for large enough n, the series is approximately geometric with a common ratio of r. Okay, cool. So let's go ahead and look at an example to practice using this theorem. All right, cool. So let's look at example 9. This is going to be fun. Okay, so we want to prove whether or not the series from n equals 1 to infinity of 3n squared over n factorial converges. And we're going to use the ratio test. We're not told to, but this example is intended to showcase that theorem that we just learned about. Okay, so let's do some scratch work, set up the steps here. So we need to compute then the limit as n goes to infinity of the absolute value of an plus 1 over an. So what do those terms look like? Well, the nth term is just going to look like, well, when n is n here, so that would be 3n squared over n factorial. So here we're using that factorial notation. So refer back to that video a couple videos ago, maybe one video ago, if you want to see some more review of that. So then what about that n plus 1 term? Well, that means wherever we saw an n here originally, we're going to put an n plus 1. So that term looks like 3 times n plus 1 squared over n plus 1 factorial. All right, so we can go ahead and plug in these terms into our ratio. So what does that look like? That looks like the limit as n goes to infinity of the absolute value. So an plus 1 goes on top. So we have 3n plus 1 squared over n plus 1 factorial. And now rather than divide by a fraction, I'm going to multiply by the reciprocal of that denominator fraction. So that means I'm going to multiply. I'll use a different color here just to really make it clear. Oops, here we go. The eraser keeps on coming out at me. Okay, here we go. So then n factorial over 3n squared. And again, I'm just multiplying by the reciprocal of our an term. Okay, so let's factor this out a little bit to see what is happening here. Or expand it out. So this is equal to the limit as n goes to infinity of what? So we still have 3. Actually, I can remove that 3. So the 3's cancel out because we're just multiplying in the numerator and denominator. So the 3's cancel. So then we have n plus 1 squared times n factorial. And then notice n plus 1 factorial is the same thing as just n factorial times n plus 1. So go ahead and think about that for a moment. So n factorial is the product of the integers 1 to n. I'll write that out. N plus 1 factorial is the product of the integers 1 to n plus 1. So we see n factorial within that n plus 1 factorial. So we can rewrite it like this, expand it out. Okay, cool. So then we still have times an extra n squared. Okay, so we can have some things cancel here. This n factorial cancels with that n factorial. We're just multiplying out a bunch of integers, so they cancel in the numerator and denominator. So let's combine some things, simplify a bit. So this becomes the limit as n goes to infinity of absolute value of n plus 1 squared over n plus 1 times n squared. All right, so let's just take a moment to pause and see if there's anything else we can see that could cancel. We should notice that we have an n plus 1 in the numerator, and it's just being squared, so we have 2 of those. And we have an n plus 1 in the denominator. So an n plus 1 in the denominator cancels with one of those n plus 1s in the numerator, helping to simplify even more. So then this is the limit as n goes to infinity of n plus 1 over n squared. Okay, so notice what happens here as n goes to infinity. Numerator and denominator both go to infinity. So using L'Hopital's rule, we can write the following. And maybe before doing that, I just want to kind of pay attention to these absolute values. So notice n here is always positive. We're just increasing n from 1 to infinity. So then numerator, denominator, always positive. So we actually don't even need those absolute values. So if you're wondering, does L'Hopital's rule work when we have absolute value? We don't even have to prove that. We can just remove those absolute values and make a note so that we justify our work. Say n plus 1 over n squared, always bigger than 0. Okay, note. Cool. So then L'Hopital's rule, here we go. We just compute now. That's equivalent to the limit as n goes to infinity of derivative of n plus 1 is just 1. Derivative of n squared is 2n. So we see as n goes to infinity, that denominator blows up, which means that entire fraction blows down or goes to 0. So this is our R value. So then what does that tell us? Well, therefore, since R is bigger than or equal to 0, but less than 1, that means our series that we started with, 3n squared over n factorial, converges. Just to remind ourselves, by the what test? By the ratio test. All right. So nice work going through that algebra. So now all that's left is for us to write a formal proof of that. So we've already done all the work, really. So now we just need to summarize our findings. So we do that in our proof. So we can say, since the limit as n goes to infinity of absolute value of an plus 1 over an is equal to 0, which is the R from ratio test. And we can say see work above. See work above. So since that limit is 0, where the 0 is the R from the ratio test, and that R is less than or equal to, or greater than or equal to 0, but less than 1, then the series, that is the sum from n equals 1 to infinity of 3n squared over n factorial, converges by the ratio test. Done. So there is our proof. We can just double check that we have everything here. So if we use appropriate justification, so we're using that ratio test. So we need to compute that limit of the ratio. We've computed it in the work above. We've shown that it's between 0 and 1, or bigger than or equal to 0, less than 1. And then we've made our conclusion that the series converges. Awesome. All right, everyone, great work going through this example and going through this entire section. Keep up the hard work.